In this video, I'm going to show you how I created this AI that plays Connect 4. And the reason I'm so excited for this is that the way this AI works is completely different than the typical game-playing AI. YouTube Connect 4 enthusiast 2Swap, whose videos on Connect 4 strategy have gotten millions of views in recent years, played against this AI. He was able to beat it, but he said, "This is fun though. It doesn't play like a typical engine. It feels much more natural. These are mistakes that humans would make." What is it about this AI that makes it play more human-like? How exactly does it work under the hood? That's the question I'm going to answer in this video, and in fact, this AI is the middle step in my video series on AlphaZero. AlphaZero was Google's AI algorithm that shattered records in games like chess and Go, and my goal is that if you watch all these videos, you will understand exactly how it works. The AI that I'm showing you today is called Monte Carlo Tree Search, and it's the basis for how AlphaZero looks into the future. It has a very organic way of building up game trees that is much more human-like than other AI algorithms. I've built all of this in the interactive Python library Marimo, which you can run in your browser, link in the description, so you can interact with these game trees and you can zoom in and see exactly how the AI is building them up. In the next video, we're going to add neural networks into this tree building algorithm, and that's going to unleash the full AlphaZero algorithm. Make sure you subscribe if you want to see that one when it comes out. Now, one of the advantages of the way this Monte Carlo tree search algorithm works is that it uses much less position evaluations than a typical AI algorithm. State-of-the-art chess engines might use tens of millions of evaluations looking at individual board positions and deciding if they're good or bad every time it makes a single move. AlphaZero, on the other hand, uses only tens of thousands. Humans have very good judgment about which moves they should completely ignore and which ones they should focus on, and they only look at hundreds. A really nice quote I found on this was from Garry Kasparov, the former world chess champion, who said, "AlphaZero is the embodiment of the cliche, work smarter, not harder." In other words, these game trees let us focus quickly on the most important positions and spend our effort there, not wasting our time on lots of irrelevant moves. And to see this, I'm going to show you exactly how it works in the app that I built. Okay, so I'm here in the interactive Python notebook, and we're going to learn how this Monte Carlo tree search algorithm works. By the way, this is all running Python, so if you want to see the code, you can click over here and toggle the view, and then you can click in and read how all the code works. That might be interesting for some of you. In any case, if you click over here, you'll go back to app view, and then we can answer the question, why do we need fancy tree search anyway? And the problem is that game trees, so a game tree consists of thinking of all the different board states that could happen in the game. The problem is it grows exponentially fast. So here's the empty board, which I have labeled node 0. No moves have been played yet, and there are 7 possible moves in a classic game of Connect 4. Where are you going to play your first move? And there are 7 responses to that move. So if I bump up the depth of this tree here, now there are, for each of those first moves, we have 2 layers deep, and now there are 7 possible responses to each of those. And if I go up to 3, then there are 7 possible responses to that. And already our game tree is looking totally insane. And the problem is our paper is only geometric, it grows with the square of the side length, but the game trees grow exponentially. They go 7 to the power of the number of moves that we have. And not only that, a lot of these moves are totally dumb. A lot of these moves would never see the light of day in a real game. So we sort of have this problem on 2 fronts that we're looking at tons and tons of moves, but most of them are irrelevant. The solution to this problem is going to be to hyper-focus our attention on only the board states that we think are promising. Board states that could actually come up in the actual game we're playing. In other words, we're going to try to identify which moves we think really might happen and which moves will never happen, and only ever put the ones that really will happen into our game tree in the first place. This is going to eliminate it down from exponentially many possibilities to something that we can handle. This is actually a lot like how humans think. So when you're playing a game of chess, you're not evaluating all the possible moves. You think of sort of like, what are the top 2 or 3 moves I could think about here? What are my candidate moves? And you think about those, and then you think about the candidate moves that your opponent could do. Monte Carlo Tree Search is going to do exactly that kind of thing, really focusing in on the most promising moves, the moves people might actually play first. So how does it work? Let's see a board state over here. So here is a very typical board state in Connect 4. This one actually has 2 moves that are okay, playing in column A1 or in column A4. The column started at 0, so 1 is actually the second column. And the other moves are quite bad. If you play in column A5 or column A6, you are going to get crushed right away because the opponent will get a 3 in a row. We're the red piece, by the way. So how is Monte Carlo Tree Search going to do this? Well, it starts out just like this, the most basic thing, having the board state we're looking at as the root node and all the possible moves that could go from there 1 level down. But then when I add more to it, it's not going to add more equally. So let's see what happens here. I'm going to show you exactly in detail how it adds nodes 1 by 1. But for now, to see the final result, let's add 1,000 steps to this tree. So 1,000 steps is a pretty significant number of steps. It's going to add 1,000 nodes to this tree. So if I press this button, run full MCTS, Monte Carlo Tree Search step, 1,000 times, and I run that, it will add all these things to the tree. And what does it say? It says maximum diagram exceeded. So what we're going to do down here, we have some controls to limit which parts of the tree we look at, because otherwise this mermaid diagram that is being displayed is overflowing the browser. So let's go down. Let's show just the top 300 nodes that it looked at. Okay, still exceeding. Let's go to top 150. So these are the 150 nodes that the AI thinks are the most likely to come up in this game. And you can see that the tree is not sort of the same depth everywhere. Parts of the tree are really, really deep. So over here, we're going like 5 or 6 moves deep. By the way, you can scroll around by using the scroll wheel. That's what I find is the best way to do it. If you hold down Shift, you go left or right, and the regular scroll wheel will take you up and down. So sometimes we're going all the way down to these like very complicated positions where we've played a bunch of moves in a row, and it's already, you know, turning into getting closer to the mid game of the Connect 4 game. But on other parts of the tree, so if you look at other parts of the tree, let's see if I can zoom all the way out and look at a part of the tree that is very shallow. Over here, all the way on the right of the tree, these moves that we said are bad moves to play at first, playing action A6 first or action A3 first, these are going to lead to you losing. And so the AI does not waste its computational resources there. How exactly is it doing that? The main difficult question that has to be answered in this strategy is, how do you identify what is a promising move and what is not a promising move? You see, the problem is, if you are kind of too greedy with what you think, you're like, I think this is the best promising move, and you only go too hard on that, then you might miss a move that didn't seem super promising at first, but maybe was more promising later. In other words, you can't be too greedy. On the other hand, you can't be too egalitarian. You can't try all the moves, so you do have to make a decision somehow. And fortunately for us, we've already solved this problem. This problem was solved by something called the UCB algorithm, the upper confidence bound algorithm, and the previous video in the series was about that. I'll give you the really quick recap of that here. So the main idea is we're going to evaluate whether or not moves are good or bad using something called random rollouts. Now, a random rollout is testing to see if a position is good or bad by just playing random moves until the end of the game. So for example, if I want to test out how good is this position, I can just play random moves, and that will bring me to a new position that looks maybe something like this. In this position, we won the game because we got 4 in a row like that. On the other hand, if I wanted to test out this position, I would play random moves, and in this case, we lost the game because blue got 4 in a row like that. So random rollouts just mean play the game randomly until completion and see who won the game. Of course, this is very noisy. You have to do a lot of samples to get some signal out of this random game playing process, but it is the basis for how we decide which positions are better than others. For example, in this case, we would decide that A1 is a better position than A6 because we won the game and didn't lose the game. Once you know what a random rollout is, I can tell you what the UCB algorithm is that decides whether or not moves are promising or not. Here's a quick recap of the UCB algorithm. The UCB algorithm, it decides which ones to run our random rollouts on. And it does it by mixing a combination of the moves that have been the most promising so far, moves that have a high average score. So if the majority of things were won by us, the average score will be large. That's the average result of rollouts from taking that action. And by average result here, I mean we usually give ourselves a +1 if we won, and we give ourselves a -1 if we lose. -1 if we lose in funny rainbow colors. And so by doing the average, we have a balance of how much more did we win and how much more did we lose. And the UCB algorithm combines the average, so it's not just the raw average. If we used just the raw average, we would be too greedy and kind of get stuck in situations where we would try things that turned out to be good but just by chance. But the UCB algorithm combines the average with some optimism bonus. So I call this thing C times 1 over the square root of NA. This is the optimism bonus. And what it does is it says if we haven't tried to move very much, so NA here is the number of times we have tried a certain action, the number of rollouts we've run from it. And if that is a very small number, we say, look, we're not really sure about that. We've only tried it a few times. We should be more optimistic about ones we haven't tried a lot yet. We don't know for sure what's going on in those cases because we haven't tried them yet. And so the UCB, the upper confidence bound score, combines high averages with adding this optimism bonus, which will make the algorithm explore positions that we haven't tried yet. And we saw in the last video, if you choose C in a certain way that depends on the total number of times you have run rollouts, then you get the so-called optimal UCB algorithm. And it's optimal in some sense that has to do with the asymptotic growth rate of the total, regret, and things like that. But for us, all we need to know is that by choosing the C the right way, we can make sure that this UCB algorithm does a good mix of trying moves that have been proven to work through rollouts and trying moves that we haven't tried enough yet. Mixing up that combination of exploring and exploiting in just the right way that we can really find out the good moves. And so things with a high UCB score, you should think of those as promising moves. They either have, been validated with rollouts and have a high average, or we haven't tried them yet, and so maybe there's something to be found there. So that's a recap of the UCB algorithm. If you want more details, you should go watch the previous video, but that's enough for what we need to do today. And now I can show you how the Monte Carlo Tree Search algorithm decides which part of the tree to expand. So here's the kind of game tree we get when we're building up our tree with this Monte Carlo Tree Search algorithm. And you'll notice that some of these nodes are highlighted. They have a bold outline that shows you that the Monte Carlo Tree Search algorithm has been selecting these as the most promising moves to be chosen. And indeed, the way it works is it just calculates the UCB score in every level, and then it picks the most promising moves based on UCB score. The actual formula that it uses is very similar to what we just saw. So in every child level, it sets the UCB score to be the average of rollouts so far. So for example, this node has an average of plus 0.12, meaning that we've won 12% more games than we've lost in trials that have started with this node. Then we add on this optimism bonus, and the optimism bonus depends on the number of times we've tried this guy. So here we've tried this guy 16 times, but it also depends on the log of the number of total things we've run from the parent, in this case, 57. So by doing it this way, as node 0 gets visited more and more, and the number of simulations here gets bigger and bigger, we add more and more optimism to every single one of its children. And what that means is that eventually, even really bad ones eventually will get tried again. So a move like this, node number 7, which has a really bad average of a negative 0.6, that means we're losing a lot more than we're winning. So it's a really bad move. We don't want to spend our resources doing that. But eventually, after we've tried everything else, and we're sort of really confident on how well everything else is going, eventually the optimism bonus on node 7 will be high enough that node 7 is chosen once again. And then maybe we'll discover that actually we were wrong before, and maybe node 7 actually turns out to be very promising if you just look deep enough or something like that. So by having this term with the log of the number of times the parent has been chosen, as that increases, it increases the overall optimism bonus, and everything will eventually get tried. So this is a balance of exploring and exploiting that works really well to do this game tree. Okay, and once you've done it on the first level, you do the exact same thing on the next level down. So to go from node 0 to node 5, we did the UCB algorithm, thinking of this guy up here, node 0 as the parent and node 5 as the child. But then once we've gone down there, we keep going down until we reach a leaf. So node 5, we now think of as the parent, and we choose one of its children, in this case, node number 10, by the UCB algorithm one more time. And by doing it this way, we sort of recursively use the UCB algorithm over and over and over again to go down, 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 down our tree and find out which ones are the most promising. And once you understand this most promising idea and how the UCB is used on multiple levels to find the most promising move, the whole Monte Carlo Tree Search algorithm is really not so complicated. All we do is we combine this selection process with a multi-level UCB. We combine that with expansion, building up our tree, adding new nodes to the tree, then simulation, that is running rollouts to get more data on what's going on. We run the rollouts from a leaf always, and then we back up the results of that rollout up the whole game tree. This is a screenshot of a typical book from this one in particular is, some people call it the Bible of basic reinforcement learning. It's by Sutton and Bartow, two pioneers of the field of reinforcement learning. And this is the kind of diagram that you'll see in a textbook or in Wikipedia. But the fun thing is I've built this for us in our app so we can see the interactive version there. Okay, I'm back in the interactive app, and now I'm going to show you in detail what actually happens when we grow the tree. And I'm going to show you these 4 steps that are used to add nodes to the tree. So the first step is the selection, then the expansion, then the simulation, and then the backup. The first step, the selection, that is what we were talking about using UCB. And the thing that it selects is highlighted here. So whatever it selects will be highlighted with these black edges. The result you're seeing here on the screen is actually the node that was added last time. So last time it added this node over here, and then it ran the rollout from there. But now we want to see how it actually works. So I'm going to select a new leaf using the UCB algorithm. So I'm going to press this button and it's going to do it. Let's see what happens. So I select a leaf and it should change what is highlighted. Okay, so in the first level, it chose, let's see what it chose. It chose node number 1. And node number 1 is what you get by playing action A0. So action A0 was chosen. And action A0 we have run 6 times before. So in the node, we're keeping track of the amount of information we've seen from it, and we've done it 6 times before. On average, we have an average of 0.00 from this node. And that means of those 6 simulations, 3 of them red 1 and 3 of them blue 1. So we don't really know who's winning the game from this situation. It seems about even. And the reason this thing was chosen is it has an average of 0 and it has an optimism bonus of 1.1. So that gives it a total UCB score of 1.1. If you look to the left of the tree, on the left of the tree, you'll notice that node number 5, by playing action A4, that actually has a higher average, 0.09. So we've won more games from node number 5 than we have from the thing we actually chose. Why is it then that we're choosing to explore this other node and not node number 5? Well, the reason is we've already done 11 simulations from node number 5. We've only done 6 from the one that we actually chose. And so we have more optimism about the one we actually chose. So that's why we actually chose this node number 1 for doing action A0 in our first level. Then from there, we keep going down. So now that we've chosen node number 1 in our first level, we can scroll down further and we can see that of the things coming out of node number 1, there are all these other options that we could play from there. And some of them we've never explored at all. So in fact, the thing we actually ended up choosing was node number 32, which we get by playing action A3. And now we're thinking of ourselves as the blue player, right? So after we play once, we now imagine what would the blue player do. And the blue player might play here in action A3. And we've never done this one before. So it has number of simulations is 0. We have never ever run any experiments with this particular node. And we have no information about whether or not it will be good or bad. So when we go down our tree, we keep going down until we reach a leaf. Sometimes a leaf will be something that has never been played before. And now what we do is we do the next step. So that was the first step, selecting. In the next step, we expand this leaf. So what we're going to do is we're going to take this leaf and we're going to add on all the possible things that could happen. We're going to add those into our tree. So we press this expand leaf and move down. And in this situation, okay, the organization of the tree, the display changed a little bit. But we have added on node number 80, which is 1 level down from node number 32, and we have moved down to that level. And now we're in a leaf that has been unexplored. This leaf for sure has never been explored, and we will now simulate a rollout from this leaf that we have chosen. So that's step 3, simulate a rollout from the leaf. Remember, a random rollout is how we decide if things are good or bad by running this random experiment. So if I run that experiment, it will now add on this little result for me. Okay, I have to find where in the tree I am. Here we are. So, and now we've done this rollout simulation, and after playing a bunch of random moves, we arrive at this position over here. All the different moves we've been played have been highlighted. Those were all randomly chosen moves. And we see that in the end, player 1 won. So there's a reward of +1 associated with this final outcome from the rollout. And finally, what we do is we take the result of this rollout and we're going to pass it all the way up the tree. So it's going to go up. It's going to be recorded in this node. So this is going to go up to 1 simulation. It's going to have an average of +1 because we won the 1 rollout. This one will also have a number of simulations 1 and a +1, but this one will go up to 7 simulations and the average will slightly increase. And not only that, the one above it will also increase. So the root node will go up from 37 simulations to 38. And that is the final step in the algorithm, just recording the results of that rollout. So if I press back up, now everything should have happened the way I said. Let's see, is this really up to 7 rollouts? So this is up to 7 simulations, and now the average has increased to +0.14. And now you'll notice this one now has the highest average, right? So before, the most promising move was node number 5 with +0.09, and now it is this one with the average of +0.14. So this one, because the average went up, now this looks really extra good. We've won another thing. So now if I run the algorithm again, I can just do all 4 steps again. I can select a leaf, and we're probably going to select that same one more time, unless I've misunderstood something. Yeah, okay, good. We selected that one again, and then we're going to expand down some more. Let's see, what did we expand down to this way? We've chosen a different child this time. So last time we did node number 32. This time we're doing node number 31, and so we can expand this one out and then simulate it, and then back up the results. And just by proceeding in this way, select using multi-level UCB, expand, simulate, back up. What happens is we're choosing the most promising moves, and those are the ones that are getting expanded. And of course, it's nice to just have the computer do it automatically. So if I could do it one time, just once, I could press this button and it will do all 4 steps. I could just keep pressing that and it would grow it one by one. Every time I press this, it's adding 1 rollout simulation to the tree and backing up the results. Or you could say, let's do it 100 times or 1,000 times, and it'll build up a whole big tree of what happens. And that is how the Monte Carlo Tree Search algorithm works. At the very end, we have this beautiful tree with the most promising moves, and we can figure out which move is the best one to play in our current situation just by which one we have tried the most often. So that is what is being shown on this bar chart over here. And on this bar chart over here, we can see that action number 1 and action number 4 were tried a lot more than all the other actions. So action number 1 was tried out of the 1,048 total simulations we ran. This one was chosen 640 times. So out of about 1,000 runs, 640 of them were all spent on action 1. Action 1 seems like the most promising move in this situation. The second most promising move was action A4, and that one was a little bit less good. So this one had an average of 0.0, while this one had an average of a negative 0.07. Nevertheless, we didn't fully rule out action 4. We kept trying it because the optimism bonus for action A4 is enough to cancel out the fact that it seems a little bit worse in the actual things we've run. So that is how the Monte Carlo Tree Search algorithm works. And if you scroll all the way down, now you can play against the AI over here. And this is a game I guess I was playing earlier. Yeah, you can scroll this game timeline slider to see how the game progressed. And over here, it shows you the final result of what the AI was thinking. So in this position, the AI played right in the middle, and you can see it thinks it's going to win almost 30% more than I am. And you can also go down here and you can have the same kind of tree exploration as before of seeing exactly what the AI is thinking at any individual move. This one's actually really interesting because it's gone really deep on this one position over here, but it has gone pretty shallow on some of the other ones. And you might notice, hey, why is it only showing two neighbors? Well, what I've done is in the settings for the display, you can have this thing to prune children and only show the children that are taking up the majority of where its simulations have gone. So in this case, I have this up to 40%. And so it only shows 2 children because 2 children is more than 40% of its simulation budget. If you bump this even further down, you can see like the most promising line is this. So this is like the most likely thing that the AI thinks will happen. Okay, so I hope you like this. I hope you'll play against the AI and try to beat it, see if it's fun. You can change its total budget over here as a slider. If you run it for 10,000 simulations, it will be a little bit slow, but running 1,000 simulations on each turn is really not that bad. And you can look into its brain. You can scroll around to different turns, and you can see what it thought about the moves overall, and then you can peek right into its brain and see what it thinks will happen later in the game. So I hope you enjoy that, and I hope I'll see you in the next video where we finally add neural networks to the mix and finally get the real AlphaZero algorithm.